Thank you very much, Florian, for this introduction. So yeah, today I will present you our experiments at Bosch France around the CVA6 and how we made it more suitable and more fit for real-time application. So these days, automotive is at a turning point with electrification, with autonomous driving and all these features. The cars are really becoming a computer on wheels. And this is a really great opportunity for RISC-V and really a great opportunity for open source hardware. That's why at Bosch France, we started to investigate what we could do in this field. And we selected one of the applications that you can already experience today. So if we consider autonomous driving, this is a far goal, this is the ultimate goal. But today you can already experience something which is part of it. This is, for example, the anti-collision system, the emergency braking system. And if you look behind the hood, for this system, what's running is a small neural network. And to run this kind of neural network, we developed a specialized system on chip, which is composed of mainly 2 CPU cores and a neural network accelerator. And that's where we wanted to introduce RISC-V and open source methodologies for the development. So we took that SoC and we made it a demonstrator by replacing the main cores that are actually commercial CPUs from another architecture by RISC-V CVA6 variants. So we have 2 variants of the CVA6 in that system on chip. One is the application one. It's a 64-bit, full Linux capable. This is a native CVA6. We have a neural network accelerator. This is a proprietary design made by Bosch Research and adapted in Bosch France. And we have also an embedded version of the CVA6, which is a 32-bit. And this is the one we are focusing about today. So first, why we did choose the CVA6? Because this is one of the most powerful RISC-V cores that you can get today on the open source community. It has a great community in Europe. So it has many contributors, and this is really what we wanted to achieve and to demonstrate that we can work in the open source context. So we chose it to replace the processor that you currently have in this system on chip, and in addition, it was reaching the performance level that we were expecting, and even more by taking the contributions from our partners, as we will see in the following slide of the presentation. Okay, so let's dig into the hardware. So currently, what do we have? This is the memory hierarchy of the CVA6. It's very classic in terms of computer architecture. You have caches, and you have, behind that, an interconnect and the memory. And on the other end, what we need when we execute real-time tasks is execution determinism. We need to be able to optimize the critical section execution time. We need to optimize the latency of the interrupt service routine, and so on. We need to speed up DSP algorithm because when you brake in your car, you don't want the braking routine to fill the cache before your car brakes. You want your car to brake immediately. So we changed a little bit the memory hierarchy to introduce what we call scratchpad, also known as TCM, tight-click open memories. So we had them in parallel with cache. And there, we plan to put the critical routine, the service routine for interrupts, and also the boot code. And as a benefit, we can get rid of the boot ROM that will be also otherwise necessary in an ASIC. And that's really interesting for an ASIC implementation, because the boot ROM is an extra step in the ASIC process. So with this scratchpad, we can get rid of that. What we did also is that if we come back to the previous structure, you see that there is an MMU that supports virtual to physical address translation. For real-time application, we don't need that kind of thing. We always work with physical address because we don't do dynamic allocation. But still, PMP is a really interesting feature. This is memory protection. So it's really interesting for development, and also it's mandatory for safety. So we changed the architecture to be able to have PMP without MMU. Okay, so that was for the memory side of things, but we also did some changes and added a dedicated bus for peripheral, because we wanted to split, let's say, the data plane from the control plane. So on the data plane, you have instruction and data. It's high boundary traffic, many outstanding transactions, out-of-order transactions, so that requires a very fancy and very high-efficient interconnect. But on the other hand, it brings you some uncertainty on the traffics. And at the complete opposite of the spectrum, you have peripherals, which requires a simple request, single request, but they have to be executed in a very timely manner. So we found out that by splitting the interconnect in two, by adding a dedicated bus that will go directly to the peripheral, we will both simplify the architecture and also increase the resilience of system and simplify the functional safety. We can have two levels of functional safety, one for the data plane and one for the control plane. So that's really a very interesting feature and simplification. Basically, in all of our experiments, the idea was to keep it as simple as possible. So the resulting address map of our system is like this, but I won't spend much time describing it because I don't have time to go into details, but again, the principle is to keep it simple. So we authorize all the access that were necessary for the application, but not more. So there are many simplifications that went over to simplify the validation and prevent deadlocks and that kind of thing. So as of today, it is still a work in progress, but we already have results that we can demonstrate, and we already achieved a demonstration of the execution timeline determinism. So if you consider running with caches, if you consider a loop of a control application, a real-time control application, the first time you enter a loop, if you have a cache, you need to fill the cache. So you have the worst time execution, and then progressively, when the cache fills up, you come up to the best execution time possible. But on the other hand, if you have scratchpad, you can directly have the best execution time possible. So you can save, let's say, the margin that is required with the cache, which is about 7%, 2.3%. So basically, you have 6% of performance lift for free. We're also working on something else, which is under development, is that with a cache, you need one wait state per access. You need first to query the tag, and then if the data is present, you get the data. With a scratchpad, you know that the data is already there, because the software engineer has to place the data for you in the scratchpad. It stays there, and it doesn't move. So basically, we can run in zero wait state, so we can also further improve the pipeline execution. But to do so, we need to modify the pipeline. It was not the initial goal, because we are not CPU designers. So it's still work in progress, but we are still targeting to work in zero wait states. OK, so that was for the, let's say, memory side of things. But RISC-V has another advantage, is that you can customize ISA to your needs without the need of a special license. So we took our neural network application, and we benchmarked it. We profiled it. And from that profiling, we found out two main time-consuming routines that we could extract. So here we have the mandatory formula. So this is the Softmax, which doesn't appear, but anyway. So Softmax is composed of an exponential. And this is required for neural network computation. This is a kind of dynamics compression, but dynamics in the audio sense. I mean, you reduce the range of the number. And it requires a mathematical exponential. So it was really a candidate for acceleration. Not much for convolutional networks, but we want to make that ready also for transformers. There are many more softmax operations in transformer. And the second operation that was time-consuming was CRC. So you may ask, why do we need a CRC? It's because, in fact, if you remember our solution made of a control processor and a neural network accelerator, both communicate through workload descriptors. And these workload descriptors must be safe. So basically, they are protected by CRC just for functional safety. So putting everything together and having the advantage of working with CVA6, the CVA6 has another advantage, is that it provides a dedicated bus called the CVX Interface, where you can attach custom processors, custom coprocessor to your needs. And that means that you can customize the ISA without having to alter the pipeline. So when you are not CPU designer, it's really a convenient way to increase the performance of your processor without having to know the internals of your pipeline. So this is really safe. So we took the benefit of this approach to develop a concept of processor library where we could design coprocessor independently, and depending on the real-time application we have, they are pretty fixed. We don't change application during the life of the product. So we can pick up a range of processors to best fit the application we are considering, the real-time application we are considering. And so we can develop them independently. So that's why we developed a wrapper to be able to choose the processor at the very late stage of the conception and make them most suitable for the application. So here, in our case, it's going to be the CRC computation and the negative exponential for the Softmax. So here we have, again, early results. So we can see that on the Softmax, we have a 5 times speedups approximately, and the CRC 8 times speedup. And putting everything together, that brings a 40% increase in terms of performance for the whole neural network computation workload. So we found out that, in fact, at the beginning, the processor was spending a lot of time doing CRC and not much benefiting from the neural network accelerator. So at the end of the day, our demonstrator will look like this. So you remember our small ASIC. It will end up like this. So we have a complete CVA6 subsystem together with this dedicated peripheral dedicated to process interrupts, so the classic plick and clint, or coprocessor. So in our case, we have 2 coprocessors, exponential and CRC. And that will become part of a bigger system connected to a complex AXI NOC for the memory system, connected also to a system-level NOC for the application CPU, and connected to our main system RAM. And you see as well, the ROM can disappear because the main processor can preload our scratchpad using that AXI NOC and the HB slave interface going right through the scratchpad. Okay, so as a summary, what we have done here in our experiments is really benefiting from open source because we were able to customize the processor to our needs as in coprocessor. We were able to customize the memory hierarchy to support real-time tasks. We are also able to increase the performance of the processor by importing contribution for our contributors. So I mentioned that this processor today has achieved 2.1 core mark per megahertz, but partners are developing a dual issue version. This is a single issue. And with this dual issue version, we can hope winning up to 50% performance and even more. We have a cache also in the system. We keep a data cache. So we'll get a more efficient data cache from our partners. And talking about partners, I would like to acknowledge everybody that made that possible. So first, the Tristan Initiative, which is funding this experiment, and also Open Hardware Group for curating and maintaining the CVA6, which made all this experiment and all this project possible. And our 2 main partners, let's say, are providing the performance part for the dual issue and also the cache. That is Thales and the CEA list. So thank you very much. So I don't know if we still have time for questions, but otherwise we have 2 posters presenting this experiment and this research that we did at Bosch. So one directly about that, and the second one on the software aspect of things. How do we seamlessly integrate a neural network on this architecture using standard flow? Thank you very much for your attention.
I think one quick question would be possible.
Yes.
What tools did you use for during development and analyzing the benefit that you got? Was it just a spike, or did you use something else?
Okay, so I can come back to the slide there. So for the coprocessor, yes, we use Spike. Where is it? Somewhere like here. So for the coprocessor evaluation, we use Spike to evaluate the performance. So we use Spike to simulate the code without coprocessor, and then we use Spike to simulate the code with processor, and then we did a ratio, because Spike is not cycle accurate, but we know from the design how many cycles our coprocessor will take, so we did a ratio to make up these numbers. You're welcome.
Good. Thank you
Thank
very much, Nicolas.